Hi dear students, welcome to my channel Education Shop. Please subscribe my channel if you haven't subscribed yet. In this video we will solve a very interesting and conceptual questions from heat transfer books by Cengel from chapter 3 problem number 71. Come to worded statement. Consider a 5 meter high, 8 meter long and 0.22 meter thick wall whose representative cross sections is as given in the figure. The thermal conductivity of various material is used in watt meter per Kelvin are Ka, Kf that is 2, Kb is 8, Kc 20, Kd 15 and Ke is 35. The left and right surfaces of the wall are maintained at an uniform temperature of 300 centigrade and 100 centigrade respectively. Assuming heat transfer through the wall to be one-dimensional, determine the rate of heat transfer through the wall, temperature at the point where section B, D, E meet and temperatures drop across the section F. Disregard any contact resistance at the surface. Well, let's come toward the concept what it says in the statement. So in this statement provided a portion of the wall that is made up of different sections. Section A, C, B, C, D, E, F, and each section's its thermal conductivity is given in watt meter per Kelvin. So the thermal conductivity. Now let's come toward it solutions and let me write the data that is provided in the state. So thermal conductivity in watt per meter kelvins are the thermal conductivity for section A is 2 and thermal conductivity for section F is also 2 and thermal conductivity for C is 20. So there is two sections of the C. There is one upper one and the lower one. Its thermal conductivity is 20 watt meter per Kelvin. Thermal conductivity of B section is 8, that is 8. Thermal conductivity of D section, this is section D, it is 15 and the thermal conductivity temperature T1 that is 300 centigrade and temperature on the other side that is T2 and it is 100 centigrade. So determine in the first case we need to calculate what the heat transfer through the wall, so the total heat transfer, and the second case in the second case, it is asking about the temperature at the point where section B, D and E meet. So where B, D and E meet. So here we need to calculate the temperatures. This is TB. TB is our requirement in the second conditions, and in the third one we need to find the temperature drop across the section F. So how much temperature drop is occur across this section F? So this is delta F, let's say. Now come toward its solution. Here in the statement if you see that the height of the wall is given, that is 5 meter, and the length of the wall is the length of the wall, that is 8 meter, and the thickness, the whole thickness of the wall, that is 0.22 meter. Remember, this is the portion of the wall, not the whole wall. If you consider, if you look at here, the wall total height is 5 meter and the height of this portion of the wall is only at 4, 4 and 4. That become 12 centimeter. Divide with 100 to convert into meters. So it become 0.12 meter height. So this section's height is basically equal to 0.12 meter. But the total heights of the wall is too much as compared to this height, that is this height of the sections that is provided in the figure. So this is not the total height wall, it is the portion of the wall and its height is 0.12 meter and the total height of the wall is h and it is 5 meter. The total area of the wall becomes, so 8 multiplied with 5, it becomes 40 meter square. Now what will be, now for the sake of simplicity we'll take the unit length to solve the heat transfers problems. So let's say this is the portion of the length whose length is 1 meter. Calculation, you consider the length of this block up to 1 meters, that will be under our observations. We will find its heat transfer throughout this section and then you multiply with the whole area ratio to find the total heat transfer to the wall. So here the length of the section is 1 meter, this is 1 meter, and this cross line represent its cross sectional area and its height is 0.1 meter. Let's multiply these two, we will get the cross-sectional area of the sections up to 1 meter length, that is 0.12 meter square. Now next we need to find the area ratio between these two areas. So the area ratio is equal to the total area of the wall divided by the area of the section. we are interested to find the heat transfer through. The total area of the wall is 40 meters square divided by area of the sections, that is in our study to find the heat transfer through it, that is 0.12 meters square. So this meter square will cancel out with this and it will give you area ratio, that is 330 point. And we know that the total heat transfer through the wall is equal to the area ratio applied with a heat transfer through the section of the wall that is under our study. So this we need to find first, and then you multiply with the area ratio and it will give you the total heat transfer through the valve. Now the length of each sections is the same, that is 1, so we can say that LA, LB, LC, LD, LE, LF, that is equal to 1 meter, because we are interested to find the heat transfer up to 1 meters only. Then we will multiply with the area ratios as we discussed previously. You will get the total heat transfer of the wall. Now let me draw the thermal resistance network for this sections of first resistance that is offered to the heat transfer is by this section, that is A. This is, let's say, RA. Then this section 1, 2, 3, C, B, C are in parallel, so its corresponding resistance will also be in parallel to the heat transfer. RC, RB, RC again. Then again 2 sections are parallel, so 2 more resistance are in parallel occurs to the heat transfer, that is section D and then section E. And then the last one is resistance is offered by this section of the, this is RD, this is RE, this is R, and finally the output temperature is T2 to observe, that is 100 centigrade. Inside wall temperatures is 300 centigrade. So we will find the total resistance that is offered to the heat transfer for each section. Now the formula to find the resistance is equal to Rx divided by Ka. First we need to find the resistance Ra. We will write in subscript A. So the thickness of the section A is 1 centimeter as it is mentioned in the diagram. So divide the 100 to convert into meter and it will be equal to 0.01 meter. And the height of this section is HA, and it is simply add these 3 fours that become 12 centimeter and divide with 100 and convert into meter. As you can see here, that is 0.12 meter. So the area of the A sections become equal to HA multiplied with L, and that is 0.12 multiplied with LA. LA is 1, so I just simply put these values in this. When you solve this on calculators, you will get the value of resistance Ra is equal to 0.04. Okay, next we need to find the resistance that is offered by section B. So we need to know about the thickness of the section B, that is XB, and it is 5 centimeters. Its thickness, divide with 100 to convert into meters, so you will get 0.05 meter, and the height of this section is just 4 centimeters. So it means that HB is equal to 0.04 meter and its length LB is equal to 1 meter as we mentioned earlier also. So the area for this section is equal to HB multiplied by LB and it is 0.04. Then the resistance RB offered to the heat transfer, it is XB, that is 0.05 divided thermal conductivity that is given in the statement. When you solve this on calculators, you will get the value of RB. Next, to find the resistance that is offered by the section C, that is RC. For RC calculation, we need XC. The XC is the thickness, that is 5 centimeters. So it means it is 0.05 meter, and its height is also the same as the B1 is 4 centimeters, so it is 0.04 meter, and its length is 1 meter. Then its area of this C section is HC multiply L, and that is 0.04 meter square. Now the RC value and X is 0.05 divide value is 0.06 Kelvin per watt. For D, we first need to calculate the thickness of the D section, that is 10 centimeter. So convert into meter, it becomes 0.1 meter when you divide it with 100. Height is 6 centimeter, so HD is 0.06 meter, and its area of this section's D is equal to HD multiply L. Now the RD value is equal to, what is XD, that is 0.1 divide value of KD, that is 15, given in the statement. And you solve this on calculators and you will get its value. If you look at the section D and E, it's the thickness of the XD and XE is equal because it is in the same dimensions. So these two sections are in the same dimension but of different material. You can say that now the R next is to find the resistance that is offered by the section F. Now the thickness of the KXF is 6 centimeter. So divide 100 to convert into meter and it becomes 0.06, and just simply do 6 divided by 100, that becomes 0.06 meter. This is the thickness of this F section X. Right here that is 0.06. Divide KF value is 2 and its cross-sectional area. Simply add this 6 centimeter and 6 centimeter becomes 12 centimeter. Divide with 100, it becomes 0.12 meter. This is the total height. So here we write 0.12 meter square. When you solve this on calculator, it will give you the resistance offered by this section, that is 0.25 Kelvin per watt. Now let me encircle all the resistance of every section. So I have encircled all the resistance of each section, so you can clearly understand what are its values, so you don't get confused about. Now we need to calculate the total resistance of this thermal resistance network diagram. First we will find the resistance of the parallel configurations, that is RC, RB, RC. These three resistance are in parallel, so we will find its equivalent resistance. Let's say that is R1, and then the resistance RD, RE is also in parallel, and you will find its equivalent resistance, that is R, and then you need to calculate the total resistance. The total resistance will be the sum of RA plus R1 plus R2 plus this RF, and when you sum this, it will give you the total resistance, and that will be R. So let's so 1 divided by R1, that is our concern to find. 1 divided by RC, RC value is 0.06 plus 1 divided by RB, that is, so here the value of RB is 0.16. When you solve this on calculator, it will give you the value of RB, and it is 0.16 Kelvin per watt. Just solve this on calculators and you will get the equivalent resistance R1 value for these three parallel configurations. Let me solve this on calculators for you, that you can easily get it. Press this button. So here is 1. How you will write that? Press this alpha button and then press this buttons. You will see X that represent the R1. Now how you will display on calculators the equal? Just again press this alpha button and then press this calc button. Now just simply put the values. 1 divided by now don't press equal button, press this equal buttons, it will give you sign error. To avoid these things, just this shift button, calc, solve for X, yes. Now press X value and it will give you value of X, and it is basically the value of R1, and it is 0.025. Similarly, we will find the equivalent resistance of RD and RE, that is R2, and it is equal to 1 over. Now solve this on calculator, we will get the value of R2, that is solve for x, yes, that's equals, and it will give you the value of R2, that is 0.0. Let me write on the notebook. As I already told you, the total resistance will be the sum of RA, R1, R2 and RF. So R1 value has been calculated, R2, RF, RA. So all the values of each resistance has been calculated. So it is very easy now to find the total resistance. So the total RT value is equal to just simply add this way. It will give you the total resistance that is offered by these sections of the valve up to 1 meter length, that is 0.35 Kelvin per watt. Now let's come toward our first requirement that has been asked in the statement, that is to find the total heat transfers occur through the valve. For that, first we need to find the heat transfer occur through these sections up to 1 meter length. It is equal to Q dot, and it is equal to, what is T1 value, that is 300, minus T2 value is 100, and the total resistance that is offered is 0.35. Now just simply solve this. So this is the heat transfer that is occurred through the sections of these valves up to 1 meter length, as I already told you at the beginning of its solution. Now to find the total heat transfers through the valves, just simply multiply it with the area ratio. So what is Q dot, that is 571.4 multiplied with area ratio. What is area ratio, that is 333.2, and to convert it to Kelvin, so you will get the values of 190.47 kilowatt. So this is the heat transfer that is occurred through the whole valve whose height is 5 meter, and this is the heat transfer that is occurred through the portion of the valve whose height is 0.12 meter and its length is considered to be 1 meter. When you multiply this heat with the area ratio, you will get the total heat transfer through the valve. I hope you understand the first requirement that has been asked in the statement. Now come to the second requirement that is asked in the statement, is to find the temperatures at the section B, D and E meet. This is B, D, E. So it meet here. You need to find the temperatures of this point, that is, let's say TB. You need to draw the thermal resistance network diagram for it. So the first resistance that is offered by this sections A, this is, let's say, resistance that is offered by sections A, that is RA. Then there is this C section, RC, RB, RC. So each sections offer resistance to the heat transfer. These three sections are in parallel. We will draw its thermal resistance in parallel also. And this is the point where the temperature is TB. Here the temperature is T1. Here the resistance offered to the heat transfer is RC. This is RB, RC. And also we have calculated its equivalent resistance, that is equal to R1, and its value is 0.025 that we have calculated previously, Kelvin per watt. Now the total resistance in this case become RA plus R1. What is RA value? That is 0.04. It simply adds it and it will give you the total resistance for the second is 0.065. The heat transfer is equal to temperature difference T1 minus TB divided by the resistance that is in between these two temperatures, that is RT, and its value is 0.065. Now just simply put the value. Now multiply this 571.4 with 0.065. You can say that 300 minus TB is equal to 571.4 multiply 0.065. So you can say that TB is equal to 300 minus 571.4 4 into 0.065. Multiply this with each others and subtract it from 300. It will give you the value of dB, 262.85 centigrade. Next is to find the third requirement, that is to find the temperature drop across the sections F. So how much temperature drop across this section is occur, that is del Tf. Let's say, since we know that Q is equal to, now simply put the values. What is the value of Q? That is 571.4 del Tf that we need to calculate in this third requirement that is asked, and the RF value is 0.25. Simply multiply this with 571.4 and you will get the delta TF value, that is 142.75 centigrade. And this is our final requirement of this statement, and it has been calculated. I hope you understand. If still there is any confusion, you can ask in the comment section. Please subscribe my channel if you haven't subscribed.